Cool. Hey, everybody, and thanks for coming out to our talk this afternoon. So our talk is called Lessons Learned from Managing Thousands of Apache Spark Clusters at Scale. And basically, the structure of this talk is that we'll tell you a couple of stories of running our monitoring pipelines at Databricks that we use to make Spark and Databricks better for our users. And then we'll try to distill a couple general principles out of this that you can use for yourselves when you're building up your own monitoring pipelines in the future.
So my name is Josh Rosen. I'm an engineer on the Spark team at Databricks, and I've been contributing to the open source Apache Spark project for over 5 years now, starting out when I was a grad student at the AMP lab at UC Berkeley.
And I'm Henry Davidge. I primarily work on the proprietary side of the house at Databricks. I'm on a team that's responsible for cluster management. And before I came to Databricks, I got my BS in computer science from Yale in 2014. And as we're sure many of you do, we both love data and Spark and are passionate about using both of these things to make better decisions and better products. And most of you guys have probably heard a lot about Databricks today at this point. But just to give you a quick recap, our founding team created Spark in 2009. The mission of the company is to make working with big data as simple as possible. And our product is a cloud unified analytics platform. So the first thing that I'll try to convince you of is that monitoring at Databricks is an interesting problem. And this primarily stems from the inherent complexity of the system. So probably many application developers believe that their system is especially complex. But I think that this is actually true about Databricks because there's many degrees of freedom. So first of all, when our users launch clusters, we let them choose their Spark version. And we actually support every Apache Spark version back to 1.3. And although most of our customers are on the newer versions, we do have people using these very old versions still in production. And we want to have a monitoring solution that works for all of these versions. And even beyond the Spark version, our users are free to choose different configuration settings. And these can actually make what happens at runtime differ a lot from customer to customer and cluster to cluster. And of course, once the cluster is up and running, our users can do whatever they want to. They have the entire Spark APIs at their disposal. And even beyond that, we let them do whatever they want inside of the containers that we use to run Spark. So they can do things like install arbitrary packages, change system configurations, really anything like that. And even on another level or another axis, we have deep integrations with the cloud provider that also provide some degrees of flexibility. So we launch all of the instances that we use to run Spark with EC2. And since we run these EC2 instances in our customer's environment, and our customers have complete access there, they can actually do whatever they want, like change network settings, do stuff like that. And although we have a few blessed configurations that we recommend, again, our customers can do anything, and this actually leads to a lot of variation between different environments. Beyond the complexity of understanding what's actually going on with our system, there's also simply a lot of data to process. So from our core services that provide the user-visible parts of Databricks, like our notebooks and our job scheduler and our cluster manager, we have over 300,000 metrics per minute. From the clusters that we run on behalf of our customers, we have over 2 million metrics per minute. This actually makes sense that it's a lot bigger, since we typically have many clusters per customer and then many machines within each cluster. And in addition to this really quantitative data, we have over 200 megabytes per second of raw logs. So this is basically what the Databricks architecture looks like at a high level. As I just alluded to, we have a couple core services that we operate in our own account and our own controlled environment that provide the user-visible parts of our cloud product. And then we run many, many clusters for our users, and this runs in their own AWS account and in their own VPC, so it's isolated from everything else.
So each of our services at Databricks produces 3 main streams of logs and metrics that we gather for analysis. First, we have fast path metrics. These are things like timers, counters, histograms that come from Coda-Hail metrics instrumentation in our code. These metrics are captured and stored in Prometheus, a time series database, for sort of low latency, basic dashboards and alerting and reporting. And so these metrics are very useful, but there are limitations to how much metadata and how much detail that we can put into these. We can't attach a lot of information to each event. In this talk, we'll be focusing on logs, and those come in 2 forms. First, we have semi-structured or structured logs, and these are JSON blobs with well-defined schemas and fields describing events. For instance, in the Databricks product, whenever you create a cluster or attach a notebook or run a command, or as we'll see in a little bit, attempt to launch an EC2 instance, we emit a structured log with details of what happened. And then finally, we have unstructured logs of the kind that are just basic text statements, what you'd get from a logging statement in your code with log4j. And all three of these log sources originating from our services are pushed to Amazon Kinesis. And so the design decision here to push logs to an external endpoint rather than having something connect to our services and pull them is motivated by service discovery problems. We have a lot of services that and processes that are sort of temporary or transient in nature. Consider the workers on our Spark cluster, for example. So it's kind of hard to actually identify all of them and regent them to get the logs. Instead, having a single endpoint we can push all logs to makes things architecturally simpler. So the output of this Kinesis stream is read by a Spark structured streaming job that's running in Databricks. And this consumes the stream and writes out every couple of minutes, every minute or so, a batch of records as Parquet files in S3. And then on the other end of that pipeline, we have a number of Spark jobs, both batch and streaming, which run in Databricks and read that Parquet in S3 and either produce more derived tables for data science and summaries like that, or run streaming queries and push out to alerting and monitoring systems. So one interesting thing that you'll note here is that on this far right side of the diagram, we have streaming alerting, but it's not running directly off of Kinesis. And the reason for this is scalability. If you want to attach hundreds of syncs to a single Kinesis source or stream, you'll eventually begin to hit bottlenecks at that point. And our latency requirements are not so strict that we need millisecond latencies here. For alerting applications, a couple of minutes of latency is at a human time scale, and that's fine for us. So by driving the streaming off of Parquet files in S3, it lets us scale out horizontally the number of streams.
Cool. So the first story that we'll tell you about is a monitoring pipeline that we set up to track AWS anomalies. And when we say anomaly in this case, we mean any failure that we encounter when provisioning a cluster that we don't expect. So as many of you who've probably worked with AWS in the past have seen, there's a lot of weird stuff that can happen when you're spinning up infrastructure, particularly dynamically in the cloud. So basically there's three major categories that issues that we encounter fall into. The first one are cloud provider limits. So AWS very reasonably imposes limits on most everything that you can do. So when customers are first onboarded into Databricks, it's pretty common for them to hit some kind of limit, perhaps associated with the number of instances that they can have running at one time of our default instance type. So this is a pretty common kind of failure mode. Another sort of failure that's a little bit harder to track down, but still pretty common, is something that generally falls under the umbrella of environment issues. So this is when Databricks is already set up and something about it breaks. So since we run everything in the customer's environment where they have complete control, this actually happens with some regularity. For instance, at a large organization, the people who use Databricks and the people who administer the account may not be the same. So for instance, someone might deactivate the credentials used by Databricks, or they might set up some sort of cost monitoring bot that terminates all resources that don't have a certain set of tags. And this causes problems and failures that then come into this pipeline. And finally, the most interesting family are bugs. And these can be bugs either on our side. We encounter these because working with some of the cloud APIs can be a little bit challenging. For instance, most of the AWS APIs are eventually consistent. So you can create an instance, get an ID back, try to describe it, and immediately get a 404 because the resource that you just created hasn't been propagated to all the servers that you may be talking to. And we also sometimes encounter bugs on the cloud provider side. And we still want to track these so that we can work through them with AWS's help. So the goal of this pipeline that we set up is to catch as many bugs as we can and alert an engineer so that we can investigate them and figure out what's going wrong and fix it for our customers, while not making the on-call engineer's life completely miserable. So the first thing that we decided, the first thing that we needed to set up when we were creating this pipeline was we set up a simple schema for each failure event. So this is basically what it looks like. It's not too important to grasp the exact details, but we have an instance ID that we can use for deduplication, and then we have a couple pieces of failure metadata. So it's not always that easy to figure out why exactly an EC2 instance launch failed. So we pass along basically every error code that we can get from AWS, and it happens to be these three fields. Additionally, we include some customer metadata so that we can figure out how many of our customers and which ones are affected. And we also track what region the failure occurs in, because often these failures are correlated based on a region, particularly in the case of a cloud provider outage. Once we have these events coming in, we set up a structured streaming query that reads from the Parquet file source that Josh was just talking about. And the first thing that this streaming query does is strip out all of the known error patterns. So we basically have a small database of error codes that we know fall into one of the first two categories, limits and environment issues. And we immediately drop those because we have other pipelines set up to alert the customer when we think that their environment is compromised in some way. For everything that's left, we consider these to be new and interesting error types that are likely indicative of bugs. And as soon as we see one of these that we haven't encountered before, we file a low priority alert. Basically, this just posts in a Slack channel or files a low priority JIRA, and the on-call engineer can look at this when they have a couple free minutes. If we begin to see this error across multiple customers, which indicates that it's more widespread, or it's happening so frequently for one customer that we believe that it constitutes a service disruption, or perhaps an entire outage, we immediately escalate the issue and someone looks at it immediately, just drops whatever they're doing and begins to investigate it. So this is one example of when this pipeline came in pretty handy. So this happened at the very beginning of May. On the x-axis here, you can see the date as well as the hour within the day. And on the y-axis, you can see the number of instance launch failures that we've encountered. So you can see at the bottom left, this is kind of what the pipeline looks like in steady state. We tend to have very few errors. But then we begin to see some launch requests that are failing in US East 1. And we see this begin to radiate out into other regions. And eventually, we have a very high failure rate. And these happen to be spot instance requests. So many of our spot instance requests were failing during this window. And then we see the rate drop off very steeply after its peak. So actually, what happened in this case is that an AWS bug caused many of our spot requests to be rejected, and actually with a very confusing error that was a little bit hard for us to track down. It basically said that we couldn't launch an instance, or we couldn't launch multiple instances with a specific set of parameters, when in fact our code was only launching one at a time. So because we got these rich alerts, and we were able to track down specific requests that triggered this issue, we could get in touch with AWS and help them debug the issue quickly. Actually, the decline that you see in the previous graph came from when we alerted AWS support, and they were able to push out a patch pretty quickly. And because we knew about this pretty early on in the process, we were also able to get in touch with our customers and communicate to them that we knew that there was an issue, and that we knew what was going on, and that we were working to resolve it as quickly as possible. So if you're a Databricks customer, you might have gotten some emails or some banners on this day. So this is kind of a fun example of how our Databricks and Spark clusters helped improve the experience of our customers using Databricks and Spark clusters.
Cool. So I'll be talking about a similar pipeline that we have set up for monitoring errors from Spark itself. And in contrast to the input data that Henry was working with, where we actually have structure and well-defined schema and fields, I'll be talking about how we analyze log4j logs produced by Spark itself, which tend to be much noisier and lack a lot of that structure, kind of complicating our analysis. So as an engineer on the Spark team, my goal is to monitor the Spark errors that are being seen by our customers. And I'd like to be able to look for long-term patterns in this data to identify trends and find new bugs. So given a group of errors, I'd like to know how frequently they're occurring, which customers and Spark versions are affected, and whether these are parts of sort of new errors we've only started just observing or part of a longer-term trend. And one of the problems with doing this is the raw data that we're working with's lack of structure means that if we're not careful, we get a lot of noise or a lot of false positives, when we really want something that's very high signal, so again, that the on-call person doesn't go crazy. So there's a couple of problems here. First, we have many different Spark versions running in production, some of them old versions. And these old versions have bugs, which are fixed in newer versions. But as long as we still have the old versions around, they'll be producing error messages. And these are bugs that we know about, and we therefore like to ignore them. However, we don't want to completely ignore a certain error pattern. We might want to know about it only for new versions. So we need conditional ignoring and filtering logic. Secondly, the raw logs we're working with are very messy. So instead of having data in nice JSON fields, it's just a string of text. And as a result, groupings of error messages that you might want to treat as a group are in fact a bunch of separate, completely unique strings. And we have to do a lot of cleaning to get these into a nice representation we can work with and aggregate. So the solution that we came up with is we've built a pipeline which takes our raw messy logs and it normalizes them, deduplicates and aggregates them, and then applies various types of time and known error-based filters to kind of give us an overview of new and interesting errors. And based on that much smaller data, we can take action. So during our normalization path, we're basically trying to recover some of the structure in those logs so we can group them together. And this basically means taking similar log messages and kind of blinking out fields and sources of variance so we can treat them as a group. A great example would be Spark sometimes experiences shuffle connection errors. And these errors would include like the IP address, the task number, the port we're trying to connect to. And as part of this normalization process, we take those different variables and replace them with placeholders or constants so we can group those messages together. During the deduplication path, we take our normalized data and do various types of aggregations over it. So this is aggregating over time windows, how frequently is it occurring, which versions is it affecting, which specific customer shards were affected, and we also carry through the pipeline a set of non-normalized examples. So if I want to kind of deep dive into a specific error, representative of the class, then I can do that. So, what I've described here is kind of conceptually very simple, but the devil is in the details in terms of getting this to scale with the volume of logs that we have. So I'll provide a brief overview of what the pipeline that we built kind of looks like. So first we have our raw log4j logs, and they have some information on where they were produced and which customer produced them. We join these with a set of information on the configuration and version history of a particular service deployment. And this actually gives us a stream of logs that have been enriched with information on service versions. So given this log stream, we first go through a fast path filtering and deduplication step. And the goal here is to cut our log volume by a couple orders of magnitude. So there's a trade-off here between speed and amount of deduplication being performed. And the goal here is to get rid of most of the duplication fast. So we apply very, very common normalization techniques here, the 80% of our pipeline. Now that we're working with a much smaller set of data, we actually now have the resources to apply a much more expensive fine-tooth comb normalization and deduplication path to grab the last 10 or 20%. So here we have a set of user-defined functions, or SQL UDFs, that apply a bunch of regexes and sort of special transformations to get rid of the last little bit of variance. We do some additional aggregation and counting, and we're left with those groups per customer, per version, per time window counts I mentioned earlier. We end up saving these out to S3 as Parquet for later analysis. At analysis time, what we do is we actually join a database of known errors, errors that we fixed in old Spark versions with the versions where we expected it to be fixed. We join that together with our stream of errors to basically surface either new bugs or bugs which are fixed but have regressed again. So at this point, we have a much higher signal. Next, what we do is we do time-based filtering as well. So I can actually join against my historical data and say, show me only new errors that we've observed today, but have not observed any time in the past week. And the sort of nice high signal output of this process then flows to many different dashboards and alerting systems. So this has actually helped us to find and prevent many bugs. And one example of this is this bug from Spark. So in this case, a user was running a SQL query, and internally it crashed with this somewhat perplexing error, which is a decimal could not be cast to a number. And what's actually going on here is in this specific Spark version, there was a bug where for certain types of decimal columns, if you tried to compute a percentile aggregate, you would occasionally hit this error in some of the execution paths. And this error is relatively infrequent. It wouldn't be on a top 10 or 100 of errors that we've seen. And was only affecting 1 or 2 customers. But we were able to proactively detect the error and quickly release a patch for it, without the customer having to alert us, which was cool. More generally, this sort of proactive error detection is very useful for cases where a bug can cause a degradation of performance as opposed to an outright crash. For instance, if a bug causes the whole stage code gen in Spark to de-optimize and fall back to interpreted execution, It's very, very difficult to spot this. It won't cause your query to crash, and you won't have a stack trace, but it's still bad. So this pipeline lets us detect and fix those problems. So we use it for monitoring, but it also plays a very valuable role in QA in preventing bugs in the first place. One thing that we can do with this framework is we can take a diff of the error profiles produced by a staging version that we're testing and a production version that we have deployed. And we can use this to quickly surface new bugs that we've introduced or ones that we fixed. So it's very useful at that phase of development as well.
Cool. So now it's worth taking a step back and trying to identify some general principles that are useful when you're building out these monitoring pipelines over really large data sets. And the first and a really helpful thing to keep in mind is that it's better to proactively structure your data. So while there are ways to impose structure on your data after logging time, like what Josh described, or some of the machine learning models that you'll probably see in many of the talks at Spark Summit, if there's something that you know you might want to monitor, it's really worth it to, ahead of time, begin to emit some structured data about it. Actually, most of the complexity in these monitoring pipelines comes from imposing structure. So if you can take that out of the equation, you can save yourself a lot of time and effort. The second is that throughout the various stages of your pipeline, you should aggressively try to make your data as small as possible. And actually, the major savings that you get is not from any sort of technical change here. Of course, it's possible to build pipelines that can handle a huge amount of data. But as you do this kind of deduplication and filtering, you end up with data that's much easier for humans to understand. That's much easier to visualize and much easier to find patterns in. And finally, it's worth setting up multiple alerting channels even before you think that you need to. So these monitoring pipelines come in most handy when you can alert yourself at several levels. So for instance, like what we talked about before, it's really useful to have a low priority alerting queue that you can just shove anything there and someone will take a look at it eventually. It's probably not critical, but you might find something interesting. At the same time, you need a pathway that you can trigger when you encounter something that you think may be a really serious customer issue, so that you can actually stop the world and invest the resources that you need to remediate it as soon as possible. So if you find this kind of challenge to be interesting, I really encourage you to stay on the lookout for other talks that people from Databricks give. We do these kind of semi-regularly at monitoring meetups or conferences around the Bay Area. And these are some slideshows from previous talks that people at Databricks have done. In particular, you might find the talk about our fast path metrics pipeline to be interesting. And that'll give you some more information about how we use Prometheus and related tools to alert on things like system metrics and stuff like that. Finally, if you're trying to build out pipelines over large data, we really encourage you to try out Databricks. We found it to be a very useful tool to make Databricks better. So we hope you do as well. There's a free version that you can try anytime. And then the full-fledged version has a bunch of features that are really useful for this. Cool. So thank you very much.
Thanks.
Awesome. So now we have a couple minutes for questions. So if any of you guys have questions, feel free to come up to one of the two microphones here and ask away.
Hello. What kind of problems you face when you try to join with the historical errors? Any join optimizations you did? Can you share your experience when you tried to find new patterns joining with the historical error logs?
I didn't catch the first half of that question, but you were asking about how we can, how that actual join between historical and fresh data works, or? Yeah, sure. Yeah, so to repeat the question, it was asking about what types of problems we've seen when trying to join historical error data with new data. So one issue that I have seen is occasionally, the process of filtering and deduplication and normalization that we've done. Sometimes we will discover that we need to add a new normalization or a new filtering strategy. So in that case, we actually have the ability to go back and reprocess our older dates to get them into the same format to make cross-date comparison easier. More generally, though, one challenge that you might find interesting is dealing with version numbers. that I might want to be able to have a concept of semantic versioning when joining against a table of known errors, for instance, or doing comparisons. So knowing that 2.1.0 is newer than 2.0.1 and is less than 3.0, dealing with this type of version comparison logic is a little tricky. One of the nice things about Spark SQL is I can actually write a Scala UDF to do this, register that into my SQL context, and then I can just do this all in pure SQL. Yeah, so the whole pipeline that I've described is all done basically in pure SQL with 1 or 2 UDFs and subqueries everywhere. So.
Just out of curiosity, what kind of cluster manager are you using in Databricks Cloud?
So inside of Databricks, we kind of use a combination of our proprietary cluster manager that actually spins up the physical resources that we use. And then within the clusters that we create that are really just resources that are available and containers that are running, we use the standalone master. OK, cool. Well, thank you, everyone. And if you have any other questions or something you want to talk about, feel free to find us afterward.
Yeah. Thanks.